Okay, so far we solved the first 4 questions in homework 1. Now let's continue with question 5, which is a true-false question. It asks us for the 4 parts of the question 5 if the statement that each part makes is true or false. Again, we have to keep in mind all those axioms and the rules that we learned for the sets and subsets and the relation between them, how they are, what's gonna be their union, what's gonna be their intersection, and all those fundamental rules that we discussed during the chapter 1. And based on those rules, because those are guaranteed rules, now we could kind of like judge that if the statement is true or false. The first one states that if the probability of set A is the twice of the probability of the complement of set A, then probability of A is equal to 1/2 or half. Okay? To start, I know you already seen the answer in the screen, but to start, I wanted to go a step by step. We are talking about the set A and its complement. So best way to kind of judge this statement is to remember about the connection that these two sets, A and A complement, would have with each other and their probability. We know that A and A complement, okay, are mutually exclusive. Do you remember? So A complement is whatever in a sample space that is not in A. So the first rule that we know about these two is that set A and A complement are mutually exclusive. Okay? Another part that we know is that the union of the two would create the whole sample space. Make sense? So because whatever element in the sample space that is not in A is in A complement and vice versa. So again, we know that A union A complement make up the whole sample space. Now that we know these two rules, let's talk about the probabilities of these set A and A complement. We don't know what is the probability of A or A complement is, but from this condition, we already know that the probability of S is equal to 1, right? So this is what we know for sure. So let's use that condition. Probability of A union A complement is going to be probability of A plus probability of A complement minus, let me do a better writing, A union A complement is going to be probability of A plus probability of A complement minus probability of intersection of A and A complement. But we already know that A and A complement are mutually exclusive, so this one is 0. So the probability of the union is the probability of the summation of those two. Okay? So if the probability of A is twice probability of A complement, you remember the previous session, we have the same kind of situation. We could substitute the condition into that formula and find that the probability of A complement is going to be what? 1 over 3. Substitute that condition to the general formula for A union A complement, and you would find the probability of A complement is 1 over 3. And if the probability of A complement is 1 over 3, that means, based on our condition, the probability of A should be 2 over 3. Correct? So that basically means this the whole statement is false. Next statement. Is there any question so far about what we did? No? Okay. Next statement says, for all A and B, probability of intersection of A and B is less or equal than probability of A multiplied by probability of B. Now, since this is a very general statement, okay, if we could make one example that shows that this statement is not going to work, then we could prove that it's false. One example would be if we have probability of A equal to probability of B, and it's going to be 1 over 2. So if they both are equal to each other, that means the intersection of them is also equal to them. If A equals to B, that means intersection of them is either A and B, right? So the probability of intersection would also be 1 over half. Make sense? But multiplication of the probability of A multiplied by probability of B would be 1 over 4, which has a paradox with the statement that part B made. So we found a situation that is not consistent with the statement, so it's false. It's not general. Any question? No? Okay. The third statement says that if the probability of A is smaller than probability of B, then the probability of intersection is also smaller than probability of B. When we talk about the intersection of two probability, again, we have to like remember the rule of intersections and those supersets. Okay, so we know that intersection of the two sets are always the subset of each of those sets. Correct? This is the rule that we could guarantee. Okay, so if intersection of A and B is a subset of A, what was the rule for the probability of these two? Then it means that the probability of intersection should be equal or smaller than the probability of that superset, set A. Does that make sense? So if this condition is true, then we already know based on the statement that probability of A is smaller than B. So definitely the probability of intersection should be smaller than probability of B. So this statement is true.
What? Right now, we're only tied back into.
Okay, guys,
as it relates
hang on a minute.
So if we
I could let them know that they are connected to.
It's a direct.
Okay, where were we? We talked about the third statement, and based on the condition and the rule that subsets and sets have, we find out that the third statement is true. Do you have any question about the third statement, or should we move on to the fourth one? No? Okay. Part D, the statement says that if the probability of A intersection B is equal to the probability of A, then probability of A should be bigger or equal than probability of B. We could also find out a counterexample if we find, because it's a very general statement, if we could find a counterexample, then we are good. And it's easy actually to find if we consider A as a null set, okay? Then, and we know that the probability of B should be a positive number, the intersection of the two, A and B, will become a null set again. See, this is one counterexample. Therefore, the probability of A and the probability of intersection becomes 0. And definitely, we could make sure that if the probability of B is positive number in our example, then therefore, probability of A is less than probability of B because it cannot be a negative number. So we are kind of like proving that this statement is false. Are we okay with that discussion yet? Intersect. Oh. Let me remind. Let me remind the definition of the two. The A union B, okay, is all the elements of A and B together. We create a bigger set and we put all the elements from A and B, all of them together, and it's going to be A union B. A intersection B means all the elements that these two sets, A and B, share with each other. So if they share any element, then they'll be having a set, which we call it the intersection of the A and B, and it would contain all the elements that is mutual between A and B, meaning exist in both of them. We consider it as a counterexample, okay, because the statement should be general, okay, but we could easily find an example. Okay, if A is null, okay, if A is null set, then definitely when A doesn't have any element, so intersection of A and B would not have any element. You know, it's could be guaranteed. So A intersection B is also going to be null set. And the probability of null set, which is the probability of nothing happening, is 0. You know, so then we could have our counterexample and prove that, okay, in this situation, for this statement, we have an example that contradicts with the statement, so the statement is false. Did I answer your question? Any other question about question 5? No? Good? Okay. So let's move to the question 6, which is actually a very good one regarding the concept. When you read the statement and the statement of the question, please pay attention to those terminology and important condition that the statement makes. Okay, so let's read it with each other. Question 6 tell us that computer programs are classified by the length of the source code and by execution time. So we have two ways to characterize, okay, a computer program. Okay, programs with more than 150 lines in their code are considered big, and with equal or less than 150 lines are considered little. We show with B and L. Okay. If a program is fast, meaning it takes less than 0.1 seconds to run, okay, and complete, we call it fast program, created by F. And if it's a slow, that means at least it takes 0.1 second. When it says try to pay attention to these words. If it's less than 0.1, is fast. If it's at least 0.1, meaning is bigger and equal 0.1. Okay, so it's at least 0.1. We call it a slow and show it with W. Now, we monitor the program executed by the computer and we observe the length and the runtime. And we find these assumptions. The probability in this experiment, the probability contains the following information. P of intersection of L and F is 0.5. What that means? That means probability of the codes is intersection. So it's a AND situation. So it means the probability of the codes that are short, okay, in a little set and are fast. Okay. Probability of intersection of B and F means the codes that are big and fast. And the probability is equal to 0.2. Also, probability of B intersection of B and W, which is big and slow, is 0.2. The first question asks us, what is the sample space of this experiment? What would be the first step to solve such a question when you have a sequence of observation? Tree diagram. Okay, so we observed the code. It could be big or short, and each of them could be fast or slow. So what would be our sample space? BF, BW, LF, LW. Make sense? Okay, now the question asks us, calculate the following probability. Probability of having, the first one is P of W. Probability of having a slow code. How we could find those probability? By considering the summation of all the intersection with set W. Does that make sense? From the tree graph, you could easily find the probabilities. Okay, let's actually do first with the tree graph and then with the rules of the probability. We said LF is going to be half, so this is 0.5. BF is 0.2 and BW is 0.2. What is going to be the probability of LW? 0.1, because all together should be equal to 1. Okay, so this one is going to be 0.1. Now, if we wanted to find the probability of having a slow code in a tree graph, we would find all the elements that have a W in their elements. So for having a slow code, either we have to have this one or this one. It's an or condition. What that means? That means you have to add those two probability together to have the probability of having a slow set, a slow condition. Now, because these 4 elements, okay, we could, these 4 elements are independent of each other. They are separated, okay? We could distinguish these 4 elements, okay? One way to look at the sample space is to partition the sample space, okay, in 4 subsets, okay, each having 1 element, okay? Now, those subsets that contains the condition of W, if we union them, what would happen? The union of the subset that have the condition of the W is going to be like the set BW union set LW, right? Because they are partition sets, we know they are mutually exclusive, so they don't have intersection. Is that clear for everyone? So the union of them is going to be the probability of both of them together, adding the probability. Does that make sense? So this is 2 ways to find the probability of W. One with tree diagram, another one with using the rules of sets and subsets. Okay, same goes for the probability of having a big code. Okay, we use the same process and we calculate the probability of having a bit code, which is the union of BF and BW. And if we want to like calculate the probability of W union B, what is the general question? What is the general formula for that? For the union of WB? The general formula says probability of W union B is probability of W plus probability of B minus probability of intersection, right? Now, we have probability of W, we already calculated that. We have the probability of B, we already calculated that. And the question is already giving us the probability of intersection. So we could calculate the probability of the union of the two. Does that make sense? Are we good on that? Any question about the solution of the question 6? That you need clarification more? No? We good? Okay. Question 7 is also the same kind of like situation. Okay. We have 2 types of cellular phone in this question. A handle phone, which we call it, which show it by event H. Okay. That you carry in mobile phones with that you carry and mobile phones with that we show it by M that are mounted in vehicles. Okay, so we have 2 types of cell phones. Phone calls also can be classified by the traveling speed of the user as fast or slow. So we have 4 types of events. Now, we monitor our situation and we observe that either we could have the either combination of these 4 events. in our situation. And these 4 events make up our sample space. Okay? The question already given us that the probability of having a fast speed is 0.5. The probability of having a handheld phones that have a fast speed, which is intersection of the H and F, is 0.2. And the probability of having a mobile phone with a slow speed, which is the intersection of M and W, okay, is going to be 0.1. Now, first, it asks us for the sample space. Same situation as before. We have our tree diagram. Either we have handheld or mobile, and each of them either are fast or slow. So, based on these events, our sample space have 4 elements of handheld fast, handheld slow, mobile fast, and mobile slow. Okay? Now, we already know that the probability of handheld and fast is 0.2. These are known. And the probability of mobile and slow is 0.1. But because we don't know the probability of the other two, we cannot find the probability of each element for now. Now, the second part asks us for the probability of W, probability of intersection of M and F, and the probability of H, having a handheld. How we could find these probabilities? We know that the probability of F that the question gave us is basically the probability of the union of H and F, handheld and fast, and the probability of the mobile and fast, M and F. Okay, so we already know, we discussed that in previous question. Why is that? We already know that the probability of F is probability of H intersection F plus probability of M intersection F. We know the probability of F. Question gave us already. We know the probability of H intersection F, also given by question. So we could calculate the probability of M intersection F. Okay, so by using that, we could calculate the probability of fast mobile phones, and it's going to be 0.3. So we have 0.3. Since we already have the 3 of the elements, the probability of elements, we already could find the fourth one, right? So it's going to be, what's going to be the fourth one? One minus the other. No, I mean, like, do you, yeah. 0.4, right? So we already know this question. So far, we find the probability of M and F. The other two are probability of having a slow phone and probability of having a handheld phone, right? So we know that from the previous question, the probability of W is going to be the union of all those partition set that involves with W condition. Okay, so probability of W is going to be probability of intersection of H and W plus probability of intersection of M and W, which we already calculated both of them, and one of them are given by question, so we could already calculate the value. And again, for H, same rule, probability of H is probability of the intersection of H and F plus probability of intersection of H and W, which we already have the numbers, so we could calculate the probability of having a handheld phone. Any questions so far? No? So are we good with the homework one? Perfect. This one? Yeah. See, in the question 6, we are observing the computer programs, okay? And we define our observance based on 4 events. Either there are big or they are little, okay? These are the condition, or they are fast or slow. So in the first experiment, we try to identify the length in the tree diagram, and we divide them between the condition big and little, B and L. For each of those results, we run the second experiment, second test, and we divide them based on the speed to fast and slow. So overall, all the possible outcome of these 2 sequence of tests, these 2 sequence of observation is going to be, as you could see in a screen, either BF, BW, LF, or LW. Okay? The question already gave us the probability of LF, BF, and BW. Okay? The only remaining parameter in our sample space is which one? LW, right? This one is the one that we don't have. But since it's the only remaining of the sample space, we could use one of the axioms that says the sample space probability is 1. So all the probability altogether should add up to 1. When we have the 3 out of 4 probability, the 4th one should be the number that make the summation equal to 1. So we could calculate the LW based on that axiom too. Okay, now when we wanted to calculate the probability of W, okay, so we wanted to see what are the possible outcome when we say slow. We want to see what are the possible outcome that had the condition of a slow in them. So either it's gonna be big or slow, or little and slow. Okay, and it's or situation. So we have to add those probability together. And when we talk about the big probability of B, we have to find all the possible outcome that end up to having a big computer program, which means either BF, big and fast, or BW, big and slow. And since, again, it's or situation, we have to add those probability together. So the probability of the union of them, or the probability of the 2 of them, is going to be the summation of the 2 probabilities. And when we talk about the union, okay, union of W and B, do not mix these condition up. Like when we talk about P of W, we're talking about the possible outcome in a sample space that have the condition of the event W. But when we say P of W union B, means all the elements that exist in and follow the condition of the W, okay, as well as the elements that follow the condition of B. Does that make sense? So to do that, we use the general formula of union, which probability of the union is probability of the first set plus probability of the second one minus probability of the intersection, because the intersection is counted twice. Okay. So by that, we could calculate the probability of W union B. Is that clear? Did I answer your question? Yes. Any other questions so far for the homework 1? No? All good. Perfect. Now, if it let me to okay. Now let's do some more example for chapter 1. Just for getting more used to the rules and kind of like the condition and how to solve the example. The first example, I'm gonna upload this file, okay, later on in the Canvas, okay, and all these example session for this week and next week, all of them I'm recording. You already, I think, know that, and I'm gonna upload that. The previous session is already on Canvas, so you could find that on the homepage. So if you wanted to like review anything or like you wanted to practice, you could again use those files and records. Now, example 1 for chapter 1. Let's say we have a fair 6 die. Okay, it's a very simple example. What are the probability of each outcome? How we could calculate the probability of each outcome? It's easy. It's 1/6. When you like think about that, it's like intuition. But the proper way, mathematical way, is to first you have to find the sample space. Okay, so we find the sample space. The sample space, the possible outcome are going to be 1, 2, 3, 4, 5, and 6. And since this is a fair one, meaning the probability of each element is equal to the other, okay? So I'm not gonna overcomplicate it, but I'm gonna give you the mindset, okay? So bear with me for this simple example. Now, this is S. We could partition S to the set A, set B, you could find out the gist of what I'm saying. Set D, E, and set F. Okay? Now, each of them have a probability. Okay? And we know that since they are partition set, so neither of them have a shared elements. The probability of the summation of the probabilities, I wish I put A1, or okay, it's okay. A to B, let's do that. The probability of set X from A to F is going to be what? The summation of all of them is going to be 1. And we know that they are all equal to each other. So the probability of each of them is going to be 1/6. Okay, so this is I know that it's kind of like this solution is overcomplicated because you could easily find the solution, but I want you to like learn the process, because in a more complicated situation you have to think like that. Okay, does that make sense? Now, so we already covered that. The next question asks us, what is the probability of the event that we have 4 or higher? Let's go back to the sample space. This is our sample space. What is the probability of having 4 and higher? It's going to be the union of the union of sets from D to F, right? Does that make sense? So all the elements equal to 4 and higher. We know they are mutually exclusive because they are partition set. So the union of them is going to be basically the summation of those probabilities, because we don't have any shared element to minus that. Okay, so the probability of 4 or higher is going to be 1, 2, 3 over 6, right? Which is 1 over half. 1 over 2, sorry, half. Now, is that clear? Okay. The next question asks us, what is the probability of event to have an even number? It's again easy. You consider the condition, okay, and you create a union of those sets that follow that condition. Now, here we don't have any shared elements, so they are mutually exclusive, or they are partition sets, okay? So when we talk about the probability of the union, we just add the probability together, but there are some complicated cases that we have shared elements, so keep them in mind, okay? So pay attention to those situation. Go ahead. Exactly. Do you remember the rules of when we talk about the counting? We had a formula, a general formula as inclusion exclusion. You remember that? We add all the probability of all sets, then minus the intersection of 2 by 2, plus intersection of 3 by 3, minus intersection of 4 by 4, all the way to infinity. Okay, so this is the rule, but the general rule, but the short version is the one that we talk about in the homework in the last 2 questions. Did I answer the question? Perfect. So basically, having even number is the union of set B, set D, and set F, right? Each of them has 1 over 6. So again, this one is going to be 3 times 1 over 6, which is 1 over 2. Make sense? Now, last question asks us if the number that we get is a square of an integer. Okay? How many possible sets is consistent? How many of those sets that we have, those partition sets that we have, are consistent with this condition? Go over the subsets again. 1 and 4. 1 is an integer of a square of integer, and 4 is also a square of integer. So we have 2 of those sets, each of them 1 over 6 probability. So it's going to be 2 times 1 over 6, based on what we talked, which is 1 over 3. Okay, so are we good on that example? Let's go to the next. Do we have time? I'm going to go fast. Okay, so I'm going to go really fast. We have a student test. Okay, you could consider that as your own grade in this course. Okay, you could get anywhere between 0 and 100. Okay, and if you get from 90 to 100 is A to 89 B, 7 to 79 C, and also we have D, and less than a 60 is going to be F. Now, the condition for the probability is that for the scores 51 to 100, okay, those events, those scores are evenly distributed. The probability is evenly distributed between 51 to 100. And the score of 50 and lower never occurs. So the probability of 50 and less than a 50 is going to be 0. So now with this condition, we try to find the probability that question asks us. The way to show it is that when we have a certain sample space from 0 to 100, okay, we divide that because we have two levels of probability here, okay? We divide it by two groups. From 51 to 100 is 1 over 50 because it's fair and we have 50 components in it, okay? And the rest is 0. Now, what is the probability of getting 100? It's one element out of that first condition, which is easily calculated, and it's 1 over 50, right? What about event A? What happened? Getting a grade A, which is from 90 to 100. We define A as 90 to 100, okay? Again, like the thing that we talk about, like using each element as a partition set, okay? The probability of A is the summation of the probability of each element. We have 11 elements. See, pay attention. It's not 10 elements. It's 11 elements. It's 90 to 100. 11 elements, and each have 1 over 50 chance. So you could calculate the probability. Having an F is from 0 to 60. But we know from 0 to 50, the probability are 0. So we don't need to count them. Okay. So the probability would be from 51 to 59. So we have 9 elements, each with 1 over 50 probability. Make sense? Same goes for the other two. I know we don't have a time. We already passed the time for the class. Okay. So the class is over. Make sure if you don't mark your attendance, you do before you leave the class, and have a rest of the day. As a great day here. Thank you.